adjust the time on the clock before starting?
What do you mean? No, you don't ever have to go by the time. That's just a picture to show you what it's about. You're going to go from just the time that's on the clock.
Yeah, the time on the clock is just to let you know how long you've been doing your experiment for. That's all it's there for. So the start time is not the time that you have in your real life right now. It's like you're working in this fictitious lab and you started at 5:45 and your reaction took until 7 p.m. to get done. So how long did it take? It took 1 hour and 15 minutes. You know what I mean? That's all that clock is there for you to keep track of the time that the reaction has been taking. How is everybody? Any particular things that I can help you with before we move on?
I'm just listening in.
Listening in?
Yeah. Like I don't have any
It is a
questions.
class session, so I have some,
Oh,
I mean,
I know.
a recitation session. I
I
have some
haven't
things.
started chapter 13 yet. So this is like,
You should probably start watching those videos pretty soon,
yeah.
like a few days ago soon, but
I was going to say like yesterday, maybe even the
yeah,
day before.
I mean, we already did a recitation where we covered some things from chapter 13, and we're
Okay.
sort of like tying a bow on that today, and hopefully
Okay.
quite a bit of chapter 14 as well.
Okay.
So that's the plan. If you guys don't have anything, then today is catch-up day. Actually, formally in the schedule, next Monday is catch-up day. So that's exam 1 review, which means that anything that we haven't finished up from chapters 11 through 14, those are the chapters that are going to be on exam 1. So we'll finish out material for exam 1 next Monday, as well as going back over anything that you want to from the first 4 chapters. That's the plan right now. Notice that exam 1 is coming up pretty quick. All right, so looks like 12 days away from now is exam 1 on the 1st of February. So be preparing for that. Chapters 11 through 14 will all be on exam 1. Sometime early next week, I'll have the exam 1 sample test up so that you can do some practice problems that look very much like the kinds of problems that you'll see on exam 1.
How many questions do you think it will be?
I haven't written it yet. Orlina, are you kidding me? I'll have a sample test up, so it'll be very similar in size. I would guess something like 20 fill in the blank, write the product of the reaction, name the compound, those kinds of questions, and then 3 or 4 essay-ish kinds of questions, like more involved free response kinds of questions. So pretty standard length. You'll have 2 hours to take the test. It shouldn't be a huge amount of time pressure.
If we've been able to do the homework pretty easily, are we most likely going to be able to complete the exam without
I think
a whole
so.
lot of
Yeah,
problems?
absolutely. The homework questions are a really good set of questions. That's why I picked them. All right. So make sure that as you're going through homework questions, you're not stopping at I got the right answer, but you're also thinking about what does this teach me in general, right? So what principle am I using to answer this question correctly? Because on the exam, I almost guarantee you there won't be many recycled homework questions. I don't do that. It'll be questions you haven't seen before, but using the exact same principles. So you'll see different molecules that you have to figure out what the product is. So it may not be an alkene that you've ever seen before that comes up on the test, but as long as you know your reactions of alkenes, you should be able to tell me what the product of a reaction of that alkene would be. Hold on, I lost my page. I lost lost my book of notes too. Where did everything go? So we talked about alkenes and also aromatic compounds, specifically benzene and some of benzene's derivatives in last recitation. The one big thing that we didn't discuss from chapter 13 were the reactions of alkenes. So I like reaction wheels, and what a reaction wheel is if I start with the same reactant and then treat it with several different kinds of, or in several different types of reactions, it's a way of keeping track of lots of different reactions in a very small space. So here is my reaction wheel for the reactions of alkenes that we have to know about. So I'm going to use this as my alkene. The first reaction that we have to know about is, what if we treat that alkene with H2 and some sort of a transition metal catalyst? So that transition metal could be palladium or platinum. Those are both really expensive. Now they're catalysts, you don't have to use very much of them, but still they're really expensive. A much cheaper transition metal that also works most of the time is nickel. So H2 and nickel is a very common variety of this reaction because nickel is dirt cheap as far as metals are concerned. So what happens is, this is called a hydrogenation reaction. And in general, reactions where we end up putting, replacing a carbon-carbon double bond with two carbon-carbon single bonds, those are called addition reactions. So we're adding an atom or a group to each one of the two carbons that shared the carbon-carbon double bond. And I think all of our examples of reactions of alkenes that we're going to learn about in here are addition reactions. So we're adding an atom or group of atoms to each one of the carbons that shared the carbon-carbon double bond. So in this case, adding H2 across the double bond means we're going to replace the carbon-carbon double bond with a pair of single bonds to hydrogen. Note that even though I'm not showing a hydrogen here and here, I have added a hydrogen each of those places. At the beginning of the reaction, I only have one hydrogen attached at that carbon. So note that there are 3 bonds shown, so there's 1 bond not shown to hydrogen. And then after the reaction, there are only 2 bonds shown to that carbon, which means that at the end of the reaction, there are now 2 bonds to hydrogen. Same thing is true here. At the beginning of the reaction, no bonds to hydrogen because 4 bonds are shown to that carbon. And at the end, only 3 bonds are shown, which means there's now 1 bond to hydrogen. I'm looking through my list to see which of the reactions of alkenes I'm supposed to teach you guys. The problem is that organic chemists that study alkenes know like 100 reactions that alkenes can do, and there's probably 15 or 20 of them that they teach you even in the majors level chemistry class, and I think there are like 4 or something like that that you guys have to know. Yeah, all right, 4. So second reaction, actually in a lot of ways very, very similar to the hydrogenation reaction. Is a reaction that we call halogenation. So in a halogenation reaction, we add some kind of halogen, and that's all it takes. Note that there's no light here required. This is also not the same kind of reaction as when we added Br2 or Cl2 and light to an alkane, all right? So in this case, instead of it being a substitution reaction, it's an addition reaction. So we are going to add a halogen atom at each one of the 2 carbons that shared the carbon-carbon double bond. So that X represents any old halogen that you could imagine. By far the most common ones used for this reaction, for a lot of reasons, are Br2 and Cl2. The reason why F2 is not used very often is because it's really dangerous to handle, and because you have to take special precautions because it's so reactive that when you treat most alkenes with F2, there's an explosion unless you do everything perfect. So Br2 and Cl2 are the two halogen species that we normally react an alkene with. So for example, if it were Br2 here, then the product of the reaction would be the one where we had a bromine at each one of those two carbons. So third in our reaction wheel is called hydrohalogenation. So in hydrohalogenation, we're adding either HBr or HCl. All right, those are the most common ones. So if we add HCl or HBr, so the X is some halogen, then in the end, one of these two carbon atoms is going to get a halogen added to it and the other is going to get a hydrogen. It turns out that the rule we use to determine which is which, if there's a difference between these two carbons, is called Markovnikov's rule. So Markovnikov's rule tells us, and I'm going to write that in the reaction conditions here, follow Markovnikov's rule. So Markovnikov's rule tells us that the hydrogen is going to add to whichever one of the carbons already has the most hydrogens. All right. Now, in this case, there are 0 hydrogens attached at this carbon and 2 hydrogens attached at this carbon at the beginning of the reaction, which means that when we do our addition, we're going to add another hydrogen here, and we're going to add our halogen atom here. So that would make the correct product of this reaction look like this. All right, our halogen atom, Br or Cl, would add at the carbon with less hydrogens. So in this case, that carbon has 0 hydrogens. And we added a second hydrogen to the carbon that already had 1 hydrogen. So the carbon that has more hydrogens from the carbon-carbon double bond, that carbon's going to get the extra hydrogen. All right. And then the last reaction in our reaction wheel is referred to as acid catalyzed hydration. All right. So in a hydration reaction, if we hydrate something, we're adding water to it, right? That's the meaning of hydration. So in this case, adding water to something means that one of the 2 atoms of the carbon-carbon double bond is going to get a hydrogen, and the other is going to get an OH group. So we're also going to follow Markovnikov's rule for this reaction. So if we decide which atom gets the hydrogen and which gets the other group, in this case the OH group, the hydrogen is going to the carbon that has more hydrogens already. So our direct product for this reaction would look like this, where the OH went to the carbon with less hydrogens and the H went to the carbon that had more hydrogens. So that is our reaction wheel for reactions of alkenes. Now, the cool thing is that because alkenes are a functional group, in other words, a small collection of atoms that always behaves the same way, no matter how big the molecule is that contains the alkene, we still can notice that they're going to react the exact same way. So for example, what if we had a really, really big molecule that was an alkene? Make a little space here. What would our product be if we did an acid catalyzed hydration on that alkene? So all the same things that are true of this acid catalyzed hydration of an alkene are true of everyone. We still follow Markovnikov's rule. All the other stuff in that big molecule, other than the alkene, we don't have to worry about that. We just have to worry about the alkene itself, all right? So which of these two carbons is going to end up with the hydrogen and which is going to end up with the OH group? What do you guys think?
It's the most substituted one, so it would be the.
So I haven't drawn in the two groups here. So where is my H going to go and where is my OH going to go?
The H is going to go on the very last carbon molecule, and the OH is going to go on the second, or the one previous.
So the carbon atom, you mean? Yes, the H will go on this carbon and the OH will go on this carbon. Why? Well, let's take a look at how many H's were on each of those carbons at the beginning. That carbon has exactly one hydrogen on it at the beginning of this reaction. We can tell because 3 bonds are being shown to that carbon. So the one that's not shown must be a bond to hydrogen. For this carbon, there are 2 hydrogens there at the beginning because I see 2 bonds to that carbon. So 2 aren't showing. Those are bonds to hydrogen. So Markovnikov's rule tells us that when we add water across that double bond, the hydrogen is going to go to this carbon, the one that already had more hydrogens, which means that the OH is going to go to this carbon, the one that had less hydrogens at the beginning. So even in a huge molecule like this, don't be intimidated by the size of the molecule. The functional group behaves the exact same way anyway, all right? No big deal. There are also a couple of reactions of benzene rings that you're supposed to learn about. Now, reactions of benzene, at least the ones we're going to learn, are all addition reactions. Oh, sorry, additions. Oh, Dr. Musk, how could you? They're not additions. So additions are where we add something at 2 adjacent atoms. Benzene reactions are substitutions. In other words, we're taking one of the hydrogens off of the benzene ring and substituting something else in its place. All right, that's what we mean by a substitution reaction. So let's do our reaction wheel for a few reactions of benzene. The first one of our reactions is one where we can add a halogen atom to the benzene ring. And that halogen could be bromine or chlorine. Now, in this case, we have to use a catalyst for reasons that you guys don't have to worry about, all right? The catalyst is really important for making the halogen reactive enough to react with benzene. Now, remember that benzene, even though it looks like it has 3 carbon-carbon double bonds, it's not an alkene, all right? For that reason, lots of reactions that work on alkenes don't work on benzene. So we have to do some special things to get benzene to react. And that's what that catalyst is there for. You don't have to memorize that at all right? But if that catalyst is there, so in this case, if we were talking about Br2 and AlBr3, that would work just fine. Then in the end, we would do a substitution of just one hydrogen on that benzene, and we would replace it with a halogen atom. If our halogen was chlorine instead, and we would have AlCl3, then we would replace that hydrogen with a chlorine atom, all right? I think we can fit one more reaction on this page, but I don't have enough space to make a wheel out of this one. That's fine.
I have a quick question.
Sure.
So in a Lewis structure, you'd be able to easily observe that it's a substitution reaction, but on the bond line drawings, you'll have to just know that it's a substitution because visually the hydrogens aren't there, so you won't see that it's being
Right. But after
substituted.
you practice
It'll
for
look
long
like
enough,
it's an addition, but you'll have to know that.
yep, you have to know that there's a hydrogen there at the beginning and not there at the end. Yeah, that's a great point. So doing bond line drawings does take practice, right? Figuring out how many hydrogens there are on a given carbon in a bond line drawing takes practice. But in the end, that's one of the reasons why I'm reminding you that this is a substitution, so that you can think, what is on this carbon that's not being shown right now? It's a hydrogen, right? At the end, that carbon now has 4 bonds. It doesn't have a hydrogen anymore. That was the atom that got substituted out. So good point, all right? We do have to practice a lot with our bond line drawings so that we can be comfortable with how many hydrogens each of the atoms have, but that's something that you have to work on, all right? We all have to be good at that by the end of this class. So the next substitution that we'll talk about is often referred to as nitration of the benzene ring. So adding a nitro group to the benzene ring means adding an NO2. I don't even want to say add. We'll say substitutes an NO2 onto the ring. So we're taking a hydrogen away and replacing it with a nitro group, an NO2. So somebody in recitation yesterday asked about, if we start out with HNO3, why is only NO2 ending up on the ring? There's a long-winded explanation for that, which I gave during the office hours yesterday, not recitation. There wasn't a recitation yesterday. But in reality, that explanation isn't required for us to learn the product of this reaction, all right? So if you're interested in how these reactions work, then majors level organic chemistry is the class for you. And we spend lots and lots of time talking about the mechanisms by which these reactions work, all right? So how do we get rid of one of those oxygens? Why is it that nitrogen is the atom that ends up attaching to the carbon? All of those secrets are unlocked when we study the reaction's mechanism. So that's how the bonds are broken and formed to make the reaction work. The problem is, for our class, we have to cover a smattering of organic chemistry and biochemistry all in 1 quarter. We don't have time to learn those mechanisms. They're intense. All right, we'll just do one more. So this is called sulfonation of the benzene ring.
Is there a sulfur in it?
Yes, there is. As a matter of fact, the group that gets added to the benzene ring is often referred to as a sulfonic acid group.
Fine.
So SO3H is the shorthand for a sulfonic acid group. If you're wondering what that actually looks like in terms of a Lewis structure, here's what it looks like. So note that sulfur here is an octet rule violator. It has a total of 12 electrons around it, and for sulfur, that's perfectly fine. The octet rule is more like the octet rule of thumb. elements that are third row or lower on the periodic table are capable of holding more than 8 electrons around them. So it's perfectly fine for sulfur. Sulfur tends to be happy with either 2 bonds and 2 lone pairs, like in the thiol functional group that we're going to go over today, or with 6 bonds and no lone pairs, like you see in the sulfonic acid. So you might wonder what happens if we try and do one of these reactions on a benzene that already has other stuff attached to it. That's a great thought. And there is a lot of chemistry that you might learn later on that would tell you, for example, what if we started with toluene, or let's do something like, what if we started with nitrobenzene? If I tried to put another nitro group onto that benzene ring, there are 3 different places where that second nitro group might go. It could go right next to the first nitro group, or it could go at the meta position, so at the 1 and 3 atoms, or at the para position, all right, at the 1 and 4 positions. So what you're not ever going to have to do is tell me where the second group attaches to a benzene that already has something on it. Don't worry about that. If you're interested in that, that's majors level organic chemistry. It's a really important part of the chapter on aromatic compounds, is what happens when we do the reactions that we're learning about on a benzene that already has a substituent group on it. So we don't have to worry about that for this class. In other words, for the benzene reactions, you'll never have a starting material other than just plain old benzene to worry about. So they're pretty easy to memorize. Any question about any of those reactions? So that's the loose ends from chapter 13. Chapter 14 is all the videos for chapter 14 are up now, but they just got uploaded today. I'm sorry, I'm a little bit out of it. We lost one of my kitty cats last night. I don't know if you have you guys seen my co-teacher Oscar, the orange cat? Has he made an appearance in our class yet? Yeah, so anyway, he passed away last night. And that was an ordeal. So I had a few hours when I should have been working on classes that I was worrying about Mr. Oscar instead. But all the chapter 14 videos are posted now. So please watch those definitely before next Monday, if not sooner. So there are lots of,
sorry.
it's all right. I mean, he's a cat. It turned out that he had a tumor and it was, you know, he didn't die in pain or anything like that. So things happen sometimes. He went peaceful. I appreciate you guys' sentiments though.
Still very sad though. Like
It is.
that's
He
your
was
buddy.
my buddy. Yeah, he was my buddy. But he definitely was not feeling real good. So
And so that's what, because you said that you thought that maybe he ate something.
yeah, I remember he was throwing up a little bit of blood. That happened to be a tumor in his esophagus. Yay.
Oh God.
It happens. Yeah, I know. I have bad luck
Yeah.
with kitty cats.
Well, I have a chunky one if you want her. She's real great. She's really sweet.
We have another cat already. Edgar is our other cat, and he's not nearly as outgoing as Oscar is, so he doesn't tend to make many appearances on camera. We're going to see how he does as an only cat, and if he is a lonesome only cat, then we'll probably get another buddy for him to play with. But we gotta let it play out a little bit. He may actually, with his personality, he's more standoffish anyway. He loved his brother, but he might actually do really well as an only cat. So we'll figure it out.
Yeah. Maybe come out of his shell a little bit more and get a little bit more attention.
Crave attention from us instead of getting all of it from his brother. So chapter 14 is an interesting chapter. It's kind of a catch-all chapter. There are lots and lots of different functional groups in it. So by my count, there are a total of 5 different functional groups that have some reactivity talked about in chapter 14. The most important one, the one that we're actually going to learn a couple of reactions of, are the alcohols. But there's a little bit to know about lots of different functional groups here. So let me make sure I screw something up here. There we go. I've got my notes outlined in a different place for chapter 14. I'm gonna find those again. Okay, so we'll start talking about alcohols. Remember that an alcohol is when we have some sort of hydrocarbon group bound to an OH functional group. All right, so what is an alcohol not? If we have some sort of hydrocarbon group bound to a carbonyl and an OH, that is not an alcohol, because even though there's an OH functional group, it is part of that larger functional group with the carbonyl and the OH. So we call that a carboxylic acid. So alcohols are when we just have a hydrocarbon group bound to the OH, all right? We can't have a carbonyl hanging out there also. Alcohols are separated into 3 different types of alcohols, all right? So based on how many carbons are attached to the carbon that has the OH group on it, we can talk about alcohols as primary or secondary or tertiary, all right? So if we have only one carbon bound to the carbon that has the OH group, then we're talking about a primary alcohol. And the simplest primary alcohol would be ethanol, where we just had a CH3 group. But we could even have a very, very long alcohol that was still primary. So the carbon that has the OH group here is only bound to one other carbon. So that is also a primary alcohol. We can have an alcohol where the carbon with the OH group is bound to 2 other carbons. So the simplest one of those would be named 2-propanol, and that is a secondary alcohol. So the bond line drawing for that secondary alcohol 2-propanol looks like this. So the carbon where the OH group is bound has 2 other carbons attached to it. Now, we could also have something larger like this. That is still a secondary alcohol because there are 2 carbons attached to the carbon that has the OH group. All right. Then we have tertiary alcohols. So here is an example of a tertiary alcohol. We'll make a bigger one this time. So that would be an example of a tertiary alcohol that also has a benzene ring in it, all right, an aromatic ring. Tertiary alcohols are called tertiary because the carbon with the OH group is bound to 1, 2, 3 other carbons. Any questions about that? So the important reason why we distinguish primary and secondary and tertiary alcohols is because they react differently from one another. All right, in the reactions that we're going to talk about of alcohols, primary alcohols make different things than secondary ones do, and then tertiary alcohols lots of times don't react with anything. All right, they're not very reactive, at least not in the reactions that we're talking about here. So when we're naming alcohols, the rules are basically the same nomenclature rules that we've been discussing for other functional groups. We're going to find the longest carbon chain that contains the OH group. And then we're going to name the alcohol using the all suffix. So instead of ane for an alkane, an alcohol uses the, I guess it would be instead of just all, it would be enol. All right. So the enol suffix. So let's do an example. That's the easiest way to learn how to name these. What if we were naming that alcohol? All right, so counting our longest carbon chain can go from here or here because we get to the alcohol as quickly as possible. So if I count 1, 2, 3, 4, we know that it's some kind of butanol because it's a 4-carbon alcohol. So a 4-carbon hydrocarbon is butane, a 4-carbon alcohol is butanol. From there, we look for other substituent groups. I also see a methyl group at carbon number 2, as well as my alcohol at carbon number 2, all right? So we locate and name the substituent group first, 2-methyl, and then we locate and name the alcohol. So we call this 2-butanol because the OH group, the alcohol, is at carbon number 2. So 2-methyl 2-butanol would be the correct name for that molecule.
I have a question.
Yeah.
Sorry, I'll put my video on. Why did you not just use the OH group as number 1 and then did a 2,2-dimethyl?
The first carbon in the longest chain. So
Oh, that makes sense.
you gotta find the longest chain that has that functional group on it. And the OH group does not have to be carbon number 1 of that chain if it's an acyclic compound. Now, Emma, if we were talking about a cyclic alcohol, then we would call this cyclopentanol. And unless there was another substituent group here, we wouldn't even have to worry about giving a locant because we know that that OH is already at carbon number 1.
Okay,
Even
makes
if there
sense.
was another substituent group here, we wouldn't have to worry about locating the OH group with a locant because it's automatically at carbon number 1 of the ring. So what if we had something that looked like this? Can you guys tell me what the name of that compound would be? Take a minute and see if you can figure it out.
A 1,4-dimethyl cyclopentanol.
1,4. Is it a methyl group? Methyl is 1
2,
carbon.
3.
How many carbons are those groups?
Oh.
I'm counting 2 carbons in each one of those
2,
groups.
4. 2,
And
4.
is it 2, 4? So if this is carbon number 1, that would be
Okay.
carbon number 2, and that's a legit way we can count either direction here because we're getting to the same place just as fast. So 1,
So it's
2, 3, 4.
2,5-diethyl pentanol.
Close.
Oh,
Is it pentanol?
Yeah, pentanol.
It's not though.
Isn't 5-a-pentane though?
the
Cyclopentanone.
cyclopentanol.
Thank you.
Darn it.
Is it cyclopentane because it's in that pentagon shape?
It's a, yes, a 5-carbon ring is a cyclopentane. So a 5-carbon ring with an OH group hanging off of it is a cyclopentanol.
Always get caught up with the forgetting of the cyclo and even sometimes like the
Anytime you
di
have a
or the
ring
tri
that is the
part.
longest chain, it is a cyclo something, all right? And you can have a ring as a substituent group too. So let's do another example here. This will be fun.
Mm-mm.
Name that? You can. I know you can do it. So we have to name those two 4-carbon rings as substituent groups, right? So if that 4-carbon ring were all by itself, what would we call it? A 4-carbon ring is
It's like, whoa.
Cyclobutane, but cyclobutane or yeah, but butane.
cyclobutane. So if that becomes a substituent group, instead of cyclobutane, it would be
Cyclobutanol.
cyclobutyl. Cyclobutyl.
Butyl.
Would it be dicyclo?
Yes, and we would have to locate both of those substituent groups too. So if I'm counting from the OH as carbon 1, that would be at 2, and this would be at 4. So this is 2, 4 dicyclobutyl. Ah, two 4-dicyclobutyl cyclohexanol.
Oh no. Oh shoot, I mean.
So a 6-carbon ring with an OH group on the outside,
Hexanol.
cyclohexanol, right?
Wouldn't be 2,5?
Is it 2, 3, 4? Yes, it is 2, 5. That's just Dr. Musk not counting carefully. Thank you. Thank you for the correction. All right, let's try one more together.
I have another question. Is it
Okay.
ever possible to say like 2 paracyclobutyl cyclohexanol?
So ortho, meta, and para are only on benzene rings, not on cyclohexane rings.
Okay.
Good question.
If it was a benzene ring, could you say 2 para to identify that the para starts at the 2 and the other one's across from it? Or
No,
is that
you would never use ortho, meta, and para unless there are only 2 functional groups on the molecule, on the ring. So that only talks about the relative position of 2 functional groups, never 3. So if I had something like this, all right, we're going back to nomenclature of benzenes a little bit, and that's fine. If I had something like this, and I wanted to name it, I could name it based on this being carbon 1 and that 4, or vice versa. It doesn't really matter. So I could say 1, 4 dicyclopropyl benzene. Or I could call it para dicyclopropyl benzene. So P represents things that are on carbons 1 and 4 of a benzene ring. All right, that's what para means. So either one of those is perfectly acceptable. I was going to draw you guys another alcohol. Actually, that's probably enough for nomenclature. I think you guys get the hang of that already. So in terms of intermolecular forces, all right, if we're talking about an OH functional group, an alcohol functional group, remember that we have a carbon bound, we have two unshared pairs of electrons bound, or not bound, that are existing on that oxygen, and we have a bond to hydrogen. So that's what we see around that oxygen there. And in terms of electronegativity, oxygen is much more electronegative than carbon, and also much more electronegative than hydrogen. So those two bond dipoles mean that for basically any alcohol, we're going to end up with a net dipole pointing toward the oxygen. In other words, alcohols tend to be very polar molecules. So because of that, the oxygen side of the molecule is slightly negative, and the side with carbon and hydrogen, the rest of the molecule, slightly positive.
Does that also mean that it can form hydrogen bonds?
Yes, so that's what we're getting to next, all right? Besides just being polar, because alcohols all have a covalent bond between oxygen and hydrogen, they are capable of forming the strongest kind of intermolecular forces, all right? So those are called hydrogen bonds. I am not the person who made this term up. I wouldn't call it hydrogen bonding because it's not actually a covalent bond between those molecules. It's just an attraction between molecules, an intermolecular force. So what that looks like is if we had, let's say we were talking about methanol and how it formed hydrogen bonding with another methanol. So what would happen is based on the fact that this oxygen is slightly negative and this hydrogen in particular is slightly positive, we can form an attraction between that delta positive hydrogen and the delta negative oxygen on another molecule, like another molecule of methane or methanol, for example. So this attraction between the delta negative oxygen on one molecule and the delta positive hydrogen, that's a very special delta positive hydrogen on another molecule, that's what we call hydrogen bonding right there. So only hydrogens that have a covalent bond to oxygen or nitrogen or fluorine are capable of hydrogen bonding. So this hydrogen is sort of a special superhero hydrogen. The reason why is it shares that covalent bond with oxygen. So why is it that this hydrogen is special? If we share a covalent bond to oxygen or nitrogen or fluorine, that makes those particular hydrogens more delta positive than any other hydrogens that we're likely to see in a molecule. And because they're so partially positive, they can form a very strong attraction to a delta negative atom on another molecule. And that delta negative atom is an O or an N or an F, another electronegative atom. So because this attraction between that particularly positive hydrogen and a delta negative atom is so strong, we give it a special name. It's the strongest kind of intermolecular attraction. We call it hydrogen bonding. And because hydrogen bonding is the strongest kind of intermolecular force, that means that alcohols that all can hydrogen bond tend to have very, very high melting and boiling points compared to alkanes that are similar in size. So let's take a look at propane and ethanol. So propane and ethanol are very, very similar in size to one another. Which means that the kind of intermolecular forces they share should be what tells us about their relative boiling points. So let's check out the boiling point of propane and the boiling point of ethanol. I think I actually remember the boiling point of ethanol off the top of my head. I think it's 78 degrees Celsius. Let's see how good my reference brain is. So I'm actually going to look up those numbers. So propane's boiling point is -42 degrees Celsius. And if I'm right, ethanol's boiling point is 78. I boiled ethanol a few times. There we go, 78 degrees Celsius, awesome. So my reference brain is intact, that's good. The important thing here is that even though those molecules are basically the exact same molar mass as one another, they're the same size, the boiling point of ethanol is a ton higher, all right? That huge difference tells us something. That means that ethanol has much, much, much stronger intermolecular forces. So ethanol is capable of hydrogen bonding, the strongest kind of intermolecular forces, whereas propane, that's just hydrocarbon, is not polar at all. So remember that we call those weak kind of intermolecular forces London dispersion forces, the ones that nonpolar molecules can have. And because London dispersion forces are so much weaker, it takes a lot less energy to pull molecules of propane away from one another and turn them into a gas. Any questions about that? So for molecules that are the same basic size as one another, the stronger their intermolecular forces are, the higher their melting and boiling points are going to be. All right, that's a really important thing that we keep on emphasizing, which means you're probably going to get asked about it on the first test.
I have a question. So for the alcohols,
Yep.
because they experience hydrogen bonding, does that mean that they are also able to dissolve ionic compounds similar to water?
Okay, so that's a really good question. There are some ionic compounds that will dissolve in low molecular weight alcohols. You also have to worry about how big the alcohol is and what other stuff is on it. So generally speaking, alcohols that are 4 carbons or less in length are soluble in water. So remember, water is really, really, really polar, right? Which means that small alcohols are almost as polar as water is. Bigger than that, though, they're not soluble in water anymore. So why would that be the case? Well, you just have to think about polarity in terms of a whole molecule approach, kind of a holistic way of thinking about polarity. If we have something like ethanol, so just a 2-carbon alcohol, that's pretty tiny, which means that the part of the molecule that's very polar, the alcohol functional group, is a significant portion of that molecule. If we have something like this, so if I were to name that compound, I would call it 1-octanol, an 8-carbon long alcohol. Most of that molecule is hydrocarbon. So we would anticipate that in terms of polarity, it would be much, much less polar a molecule than ethanol. Both of them are capable of hydrogen bonding, but we have to look at the whole molecule, not just this little piece of it, when we decide how polar or non-polar it is.
So is that kind of like a phospholipid where there's a polar head, but non-polar is the majority of the molecules?
This would be, this would function not very well, but it would sort of function as a lipid. All right, it would. As a matter of fact, cholesterol, one of the types of lipids that most students learn about in biology, has an OH group as its polar head group, and then a bunch of hydrocarbon rings as the non-polar tail.
Okay.
So the shorthand version of that is alcohols of 4 carbons or less are water soluble.
On the slide that you have, it actually says alcohol 6 C's or less. So 6 carbons or less. Yeah.
No. Pentanol is not water soluble, at least not as I remember. 4 carbons or less. I won't be picky about that anyway, right? So if I'm going to give you a question about whether something is, I don't like it. I don't like that at all. So
Okay.
Orlina, that in terms of, I probably should say something even more stark than just water soluble, because honestly, solubility is a relative thing. So what do I mean when I say soluble? When I'm talking about alcohols of 4 carbons or less, it might even be better for me to say that they're miscible with water, which means that I can mix them with water in any proportion, anywhere from 10% of the alcohol and 90% water to 90% of the alcohol and 10% water, and they'll dissolve in one another in any proportion. That's what miscible means. When you get to things that are 5 and 6 carbon long alcohols, then they're still sort of soluble in water. So some of the alcohols will dissolve, but they're definitely not miscible with water anymore. All right. So solubility is not as much of a yes, no thing as it is a relative thing. How soluble is it? How much of 5 carbon alcohol, how much of 1 pentanol could we dissolve in a liter of water, right? It's not going to be nearly as much as a 3 carbon alcohol. And that's why I prefer the 4 carbons or less thing, because it's more
Well,
of
I
an,
just noticed as you were saying that, yeah, I just noticed as you said that it said 6 carbons or less are soluble. So like, I always like to make sure my notes really match more along the lines of like what you're saying, because your tests are going to probably be more of like what you're saying rather than what the book thinks.
and I probably wouldn't be super picky about this anyway. It would probably come up in a question like, which one of these 2 alcohols would you expect to be more water soluble? All right. So it's the principle without making you memorize a specific number. Does that make sense?
Yeah.
That's what I'm going for. Principle's always way more important than memorizing the little fact to me.
So I'm trying to piece this back to other chemistry classes. So for if you were able to put some sort of colorant dye or something onto one of these carbon molecule, one of the carbon alcohols, and it was a very short chain, like four or less, and you mixed it with water, it would look like a solution, or a solution, not a homogeneous mixture, because it's fully dispersed. But a really long chained carbon, if it had some sort of dye or colorant to it, the densities would separate.
Don't worry about the colorant. You can see 2 separate layers form if you mix a significant amount of like
Okay.
hexanol
The
and water together.
Wouldn't it be like oil and water? You
Yes,
see the
they
separation of
They
layers.
wouldn't be miscible. They wouldn't completely mix together. And that's true, I think, all the way down to 5 or more carbons in the alcohol. They'd form 2 layers. They would not completely mix with one another. So a 4 carbon alcohol or less would be miscible with water, which means that no matter how much of the alcohol layer we had and the water layer we had, once we shake them together, they all form 1 layer. They're homogeneous.
Okay. So water can disrupt the ionic bonds, and well, it can form hydrogen bonds around ionic compounds, which then
So let's talk really quick about what water does when it dissolves ionic compounds. All right. If we look at a solid like sodium chloride, if that solid ends up dissolved in water, then the ions end up dissociated from one another, separated from one another. And the reason that happens is because water in particular has that very delta negative hydrogen or oxygen that can form a strong attraction to a positive ion like sodium. So what ends up happening is you get this shell of waters that surround positive ions, and the oxygen of those waters is what's interacting with that positive ion. Very similarly with the chlorine ion, the negative ion, we have those delta positive hydrogens that end up forming attractions to the negative chloride ion. So that is why a lot of ionic compounds will dissolve well in water, is because water is a good enough solvent to be able to surround them with a shell of solvent molecules. And you can see that the way that that surrounding works depends on whether you're talking about a negative or positive ion. So imagine instead we're talking about ethanol, all right? Ethanol
Only has one of those special hydrogens, not two like on water.
exactly. So particularly when we're trying to surround a negative ion with ethanols, it doesn't work very well because that hydrocarbon tail is not very polar. All right. So we just don't have enough delta positive atoms to efficiently surround negative ions. So most ionic compounds are not very soluble in alcohols for that reason.
Okay.
That's a really good question. It's not something I get asked very often either. There are a very small number of ionic compounds that will dissolve a little bit in methanol. All right. We can take advantage of that. So sodium iodide, NaI, will dissolve to a small extent in methanol. That's actually a really, really useful thing if you're thinking about reactivity in organic chemistry. So it's one of the ways that we can introduce I- onto hydrocarbon by substituting another halogen. All right. You don't have to worry about that reaction, but there are examples of ionic compounds that are slightly soluble in methanol or sometimes even ethanol, but any bigger alcohol than that, it's probably a no-go.
Okay.
And you can, I mean, it's totally obvious why when you look at how water is able to dissolve ionic compounds. The reason why is that those oxygens can form a shell around positive ions and the hydrogens form a shell around negative ions. So if we take away the hydrogen from one side of the water, it doesn't do the same job nearly as well.
Okay. That makes sense.
Yeah.
Thank you.
Yeah. We haven't named any alcohols with more than one OH group, so let's try that. What will we name this compound? So what's your longest chain in there?
Butane. No.
Is it? I'm counting 1, 2, 3, 4, 5 carbons long.
Yeah, 5. Sorry.
Excuse me. So pentane is our longest chain. And we have 1, 2, 3 alcohol functional groups that occur at carbons 2 and 3 and 4.
Pentatriol.
Very close.
Oh,
2, 3, 4 tripentanol.
pentanol trial, not pentatriol.
Pentane
Okay.
triol. Pentane triol. So remember, this is very similar to if we had a diene like this. So that would be 1, 2, 3, 4, 5. So this would be 1, 4. Pentane or pentadiene.
The dying.
When naming alcohols, it's always going to be at the, like, trial will always be at the end. It won't be in front of the pen.
Yes, that's correct. The di or
Okay.
tri, if there are 2 or 3 OH groups, always comes right before the all.
Thank you.
You're welcome.
On that second bond drawing, that those OH are the double bonds?
What?
On the second one you drew, the double bond, that's just a carbon with a double bond, right?
Yeah, those are alkenes. So I was trying to show you like the the similar thing that we do if there's more than one carbon-carbon double bond to what we do when there's more than one OH group. So we use a similar thing. We use the prefix right before the suffix that tells us what functional group it is. So we have to say how many of the functional group and then what the functional group is. So there are 3 alcohols in that molecule. There are 2 alkene functional groups in that molecule.
When you get a Santa molecule, like a trial, does that increase its miscibility?
Yes, diols and trials tend to be very, very, very soluble in water. All right. As a matter of fact, a class of molecules called, well, I guess in general, carbohydrates have lots and lots of OH groups in them, and they tend to be incredibly soluble in water. So when's the last time you tried to make sweet tea? Everybody from the South knows that the right way to make sweet tea is you warm your tea up until it's really nice and warm, and then you dissolve as much sugar as you can in that tea and then cool it back down in the refrigerator. When you do that, you can dissolve a metric crap ton of sucrose into that tea. And the reason why is because sucrose is a carbohydrate. It has lots and lots of OH groups. So in terms of its polarity and its ability to hydrogen bond, it's very, very similar to water in a lot of ways. Now, it doesn't melt and boil at the same temperatures as water because it's a lot bigger in molar mass, but it does have similar functional groups. So it's very soluble in water.
What
Husband loves drinking that during the summer.
Ugh.
Oh, sweet. What is
Cavities.
it called when it's super concentrated? Like the chemical
Super
reaction that
saturated.
you're conducting.
Yeah, super saturated. It's where like there's more dissolved than should be dissolved. And if you upset that balance a little bit, it will all crash out of solution as a precipitate. Yeah, you can make sweet tea solutions that are like super saturated with sugar. That's also the way that you make rock candy is you super saturate an aqueous solution with sugar, and then you hang a string in the solution and just let it sit still for a while. And the sugar starts to form crystals on the string, and then those crystals build. And when you pull the string out, you got a big crystal full of sugar to lick on or just look at because it's pretty.
Stir it into coffee.
Yeah. I suppose that's true, but like you could only really do that once. I wouldn't want to like use a little bit of my crystals and then pull it out wet with coffee on it and then use it again later. Gross.
They have individual serving sticks like that. Like
That already have the
tiny-
sugar on them?
Yeah, individual serving twizzle sticks of sugar. Very fancy.
That's really fancy. Yeah.
Yeah.
We're not going to talk too much about carbohydrates in chapter 14. They do represent a very important class of molecules that have alcohol functional groups, but there's an entire chapter in our biochemistry section dedicated to carbohydrates. So we'll talk more about them when we get to that chapter. All right. The last thing that I want to talk about before we're done tonight, and we can finish up our discussion of the rest of the functional groups from this chapter next Monday is fine. All right. The other ones won't take near as long. I do want to talk about the reactions of alcohols before we leave tonight. So the reactions of alcohols that we're going to focus on will be oxidizing alcohols. All right. So when an alcohol oxidizes, it depends on what kind of alcohol it is to figure out what it turns into. So when I talk about oxidation, a quick way to think about that most of the time in organic chemistry is when we're oxidizing, we're getting rid of bonds between carbon and hydrogen or oxygen and hydrogen. and we're replacing them with either carbon-carbon bonds or, in this case, carbon-oxygen bonds. So for primary alcohols, if we treat them, oops, that's not a primary alcohol. So there's ethanol right there. So 2 carbons with an OH functional group. If I treat that ethanol with an oxidizing agent, and the most common oxidizing agent that I can think of to oxidize alcohols is potassium dichromate. You don't have to know why it's a good oxidizing agent, but it really is. So different kinds of formulations of this compound are called Jones reagent. If there's one thing that you should learn from this class about organic chemists is that lots of them have enormous egos. So if they come up with a really good reagent to do a reaction with, they want to name it after themselves. So the person that figured out that dichromate salts were really good at oxidizing alcohols started calling it after his last name. And when that reaction was popularized in the chemical literature, probably close to 200 years ago at this point, it became known as the Jones reagent. So all the versions of this that are similar to potassium dichromate, another one that does the same thing is chromic acid, HCrO4. So if you dissolve this into aqueous solution, this is what you end up getting anyway, all right? So those are all called some version of Jones reagent. Now, the cool thing that happens with these alcohols is they're oxidized, but they're oxidized twice. So right now, you can see that there are 2 hydrogens attached to that carbon, and I'm drawing them out so we can see what happens to them. And there's a hydrogen attached at the oxygen. So the first step in oxidation is going to be to remove this hydrogen and to remove the hydrogen attached to the oxygen and instead create another bond between carbon and oxygen. In other words, we're going to turn that alcohol into an aldehyde. So the problem is that Jones reagent also oxidizes aldehydes. So we can never get an aldehyde as our final product when we oxidize a primary alcohol, because as soon as the aldehyde is formed, the Jones reagent keeps on reacting with it and oxidizes it again. So the final product of oxidation of a primary alcohol is a carboxylic acid if we do the oxidation with Jones reagent. So it wouldn't be a correct answer for us to give this as the product of the reaction, because we can never end up with an aldehyde from oxidizing a primary alcohol with Jones reagent. Now, the cool thing is, a long time after the Jones reagent reaction was come up with, people started thinking, wouldn't it be nice to have a reagent that we could use to turn an alcohol into an aldehyde, but then not keep on oxidizing it all the way to carboxylic acid? Now, this is a reaction that is not in your textbook, but I think it's really important just to show you that there's more than one reaction that we can do with each of these functional groups. In fact, there are like hundreds of reactions that we can do with alcohols. They're very versatile functional groups. So I'm just going to show you one more oxidation of primary alcohols. If I treat a primary alcohol with PCC, that's the name of the reagent. The reason that I don't give you the full name is because you don't want to memorize it. It's pyridinium chlorochromate, all right? So PCC is a special oxidizing agent that will only oxidize primary alcohols to aldehydes. It will not keep oxidizing the aldehyde to a carboxylic acid. So based on which choice of oxidizing agent you use, you can turn a primary alcohol into a carboxylic acid, or you can turn that primary alcohol into an aldehyde. That's a lot of versatility.
What's being reduced?
The oxidizing agent is the thing being reduced. So in the Jones reagent, the chromium atoms start out at a +6 oxidation number and end up at lower oxidation numbers. So it's actually a mix of different oxidation numbers of chromium that result depending on how much of it you put in. But chromium is the atom that gets reduced in this reaction. And PCC, pyridinium chlorochromate, it's also chromium in here that gets reduced. But because of the structure of this reducing agent, it will not oxidize aldehydes. It's amazing. There are lots and lots of other oxidizing agents that are becoming more popular. For example, primary alcohols are often oxidized to carboxylic acids now using bleach. All right, like over-the-counter bleach solutions. That is called a green oxidizing agent, and that's because it doesn't give us any very harmful byproducts when we use it. So chromium salts are heavy metal salts. They're very, very toxic. These reagents work great. They've been used for 100 or more years, but they give us toxic byproducts that we have to store or dispose of. That's bad, right? If we use bleach as an oxidizing agent, the byproduct of that at the end is just salt water, which is great. So lots of times a new focus on oxidizing agents is green oxidizing agents that the products are not harmful of, all right? So you could do this reaction with bleach if you handled it the right way. It would work. But I'm just teaching you the first two oxidizing agents that everybody in an organic chemistry class would learn about. And I'm just telling you that there are more sophisticated ones that don't have the toxic byproducts. So what if we're not talking about a primary alcohol, but a secondary alcohol instead? For a secondary alcohol, note that at that carbon, there is one hydrogen. So the thing with secondary alcohols is there's only really one way to oxidize them, and that's to get rid of the hydrogens on the oxygen and the carbon and create another bond between carbon and oxygen. So in this reaction, it doesn't matter which of these two oxidizing agents I use. It could be Jones reagent, or it could be PCC. They both give the exact same product. So secondary alcohols always oxidize to form a ketone when we treat them with oxidizing agents. Importantly, tertiary alcohols, they don't oxidize. So let's look at an example of a tertiary alcohol. Can you think about why a tertiary alcohol might not be able to be oxidized very well? What's missing that's an important part of the oxidation reactions that we've seen for primary and secondary alcohols? With the tertiary alcohol, there are no hydrogens bound to that carbon. So because of that, there's no carbon-hydrogen bond to break along with the OH bond to break. And because of that, because there's no hydrogen attached here, that's why we can't oxidize tertiary alcohols. Any questions about that? So let's take a look at a couple of examples. So tell me what the correct organic product of this reaction is. that reaction and what about that reaction? I heard that sigh.
Is the oxygen on the last one, is that a 7 or a 2?
7. Yeah, K2Cr2O7, that's potassium dichromate. So that's one of the versions of Jones reagent. All right. This H2CrO4 chromic acid is also a version of Jones reagent. They do the exact same thing. So you could see it like this, or just Jones reagent might be written there. All of them do the exact same thing. So what kind of an alcohol is it in this molecule? Is that a primary alcohol or a secondary alcohol?
Primary.
Primary.
Yep, because only one carbon is attached to the carbon that has the OH group. So that's a primary alcohol. So if we treat a primary alcohol with chromic acid, the Jones reagent, we're going to oxidize it all the way until it becomes
carboxylic acid.
A carboxylic acid. What kind of an alcohol is this? So on the carbon that is attached to the
Secondary.
Yep, there are 1, 2 carbons bound at that carbon with the OH group. So secondary alcohols, when we oxidize them, it doesn't matter if we oxidize them with PCC or Jones reagent. In the end, they are going to make ketones. Now, I put an alkene functional group in there as well, but that is not the functional group that gets affected by PCC or oxidizing agents. So because of that, we have to know that PCC is what we use to oxidize alcohols. So that is the functional group that's going to get transformed by that reagent. So the other parts of the molecule just get left alone. But the alcohol is oxidized to a ketone, our new functional group. Now this one is extra hard, all right? The reason it's extra hard is I put a functional group in this molecule that also gets affected by Jones reagent. So we know that Jones reagent takes primary alcohols and oxidizes them to aldehydes, but it then oxidizes aldehydes to carboxylic acids as well. So the correct product of this reaction is one where we have oxidized both the aldehyde on this end and the alcohol over here. So the Jones reagent oxidizes aldehydes to carboxylic acids, and it oxidizes secondary alcohols to ketones. It did both those things. So when I look at this, one of the questions that's a common question here is, how do I know I have enough of the oxidizing agent to do both things? And the answer is, if I didn't specify how much there was, just assume that there's an excess amount, enough to do any reactions that that molecule is capable of. Any questions? So how did you guys feel going through the first lab using the instructions, the written instructions with pictures? Did it work okay?
I liked it.
So what I'm going to try to do, because I'm honestly just not feeling super good today, I'm bumming pretty hard. I'm going to see if you guys can get through the second lab without me doing a video lab tutorial for it. Just
It's
following
really
the
simple.
written instructions. And if you can't, then I'm happy to cover those in office hours. And if somebody asks, I'll just film it while I'm going through it and I'll post it then. All right.
The next two labs are really simple as long as you follow the directions.
Yeah, I think they're pretty simple too. So you've already learned how to do thin layer chromatography, which is the way that you're monitoring how the reaction's proceeding. And that's the similar thing to the first lab that you're going to be doing for the next couple of them also. Okay, if you guys don't have anything else, then when we come back next time, which will be next Monday, we will cover the remaining functional groups from chapter 14. The cool thing is we've covered almost all the reactions in chapter 14 already. So there's very little reactions left to cover. We just have to talk about a little bit of the chemistry of alkyl halides and thiols. Thiols are super smelly. So if you've ever smelled rotten egg, that's a closely related compound. H2S is the compound responsible for rotten egg smell. So it's basically a thiol without an alkyl group, sort of the water version, but with sulfur replacing the oxygen. Yeah, and lots of small thiols are really stinky. Like skunk smell is a thiol or a mixture of thiols. Natural gas, when you smell natural gas, you're not smelling the natural gas itself. That's odorless. Gas companies actually dose a little bit of a thiol into that to make it stink so that you can tell when there's a gas leak. So anyway, chemists that work on thiols tend to be chemists that don't have very many friends because nobody wants to be near them because they smell like skunky thiol all the time. And it doesn't wash off of your clothes very easily. So you've got to like wash your clothes in nice hot water, or I'll teach you a little bit about how you can get rid of that thiol smell more easily. So if you've ever anybody in class been sprayed by a skunk before?
No.
Don't raise your hand because I can't see everybody at the same time. But if you've never been sprayed by a skunk before, it's awful. It smells terrible. What's that?
Aren't you supposed to use tomato juice as an acid?
Yeah, vinegar or tomato juice work okay for getting the smell out, but that's more just getting the thiol, which is somewhat polar, to dissolve a little bit better in the aqueous solution. There's actually a way to actively de-stinkify thiols using oxidation reduction chemistry instead. So we can talk about that next time we're together. If you ever get sprayed by a skunk, rinse yourself off really, really well first, and then we'll talk about what chemical you can use to actively get rid of skunk smell. All right, so that's something to look forward to for next week. Any more questions before we're done? Thank you guys very much for all the well wishes about my kitty cat. So yeah, I super miss him, but.
All right for your loss.
What's that, Juan?
All right for your loss.
Thanks, man. I appreciate that. All right, you guys have a wonderful night, and I will see you next Monday.
Thank you.
Bye.